Welcome to AP Biology. I want to talk today a little bit about enzymes and how they lower the activation energy of a chemical reaction. So let's start out by defining a catalyst. A catalyst is a chemical agent that speeds up a chemical reaction without being consumed by the reaction itself. So what I have here is my old contact lens case from when I used to wear contact lenses. So you'd take out your contacts and you'd put one on this side, and there'd be an identical side on the other where you'd put your other contact. And then you'd put hydrogen peroxide into this case and then close it up and let it sit for a while. Overnight usually is what I did. And so hydrogen peroxide, that's the same lab that we just did a few days ago. So hydrogen peroxide will break down to water and oxygen. I'll get two of these and two of these. And this thing is not alive. This is a disc, a catalytic disc. I think it's made out of platinum. Anyway, this disc catalyzes the reaction. So catalytic disc, it's got platinum in it, and it catalyzes this reaction to take the reactants, hydrogen peroxide, to become water and oxygen. And you can actually see it working because there's all these bubbles in here. That's the oxygen. And then in the morning, it would be water, and it would be safe to put that in my eyes, as opposed to hydrogen peroxide, which you shouldn't put in your eyes. So a catalyst is something that speeds up a chemical reaction. An enzyme is a biological catalyst. So the enzyme that we used in lab was, peroxidase that we got from turnips. So an enzyme is a biological catalyst. So just like all squares are also rectangles, but all rectangles are not necessarily squares, same thing, all enzymes are catalysts, but not all catalysts are enzymes. So this is a catalyst, but it's not an enzyme because an enzyme is living. It is made from a living thing. It's biological. So all the catalysts in the plants and the animals and the bacteria that you can't see here, they're all enzymes, which are a type of catalyst. So enzymes are usually proteins, and so you might remember a lot of stuff about proteins, and you might not. So if you don't remember a lot about proteins, I want you to go back and study those notes a little bit, because all of the stuff that you learned about proteins, the primary structure, secondary structure, all that stuff is still important. So as a reminder, proteins are made out of amino acids. So you'll have a long string of amino acids. Each amino acid has a nitrogen to a carbon to a carboxyl group here, carbon with an O, I always say, nitrogen, carbon, carbon with an O. Nitrogen will have some hydrogens on it, and then it will bond to another amino acid, and you'll do a dehydration synthesis reaction, taking the H off one and the OH off of another to put those together. Anyway, the amino acids all have an R group, and that R group differs from amino acid to amino acid. So some R groups are positive, some are negative, some are hydrophobic. So all that stuff that you learned about proteins before is really applicable to this unit too. Okay, so here's just an example of a particular, I think it's going to switch. This is just an example of a particular reaction. So in this particular reaction, you can see, I think I have to change colors. Okay, you can see the reactants right here. So the reactants come before the arrow. It's what you start with. And so one of the reactants is sucrose. You might remember os means a sugar. And you can see there's two sugars bonded together here. So this must be a disaccharide. And then there's water, which we're going to need for this hydrolysis reaction. Remember, hydrolysis is when you have water and you break an OH off and put it on one side, and the H off and you put it on the other side, and then you get these products. So that's a hydrolysis reaction, hydro for water, lysis for breaking. And another thing that I want you to notice is that this reaction is catalyzed by this enzyme sucrase. So we usually name enzymes with ACE. So if you see a word that ends in ACE, you can bet it's an enzyme. There are enzymes that don't get named this way, unfortunately, but usually the way we name them is we base it on the substrate, like sucrose, and then we just add ACE to the end of it. Okay, so hydrolysis of sucrose, the sugar, by the enzyme sucrase, ACE, is an example of an enzyme-catalyzed reaction. One other vocab word that I want you to have is substrate. It's supposed to be an R. So a substrate would just be the reactant if you're using an enzyme. So an enzyme works on the base material, the substrate, which is the same thing as the reactants. If you have an enzyme, you use these words interchangeably. Okay, activation energy. We talked about this in our last unit. The activation energy is the amount of energy you need to get started in a reaction. So it's sort of like climbing a mountain. So let's look at that over here. So let's say you have some reactants right here, and they have a certain amount of energy. You have to always put in a little bit of energy to break bonds. And then what you have here is the transition state. In this case, you've broken all the bonds. You don't always break all the bonds, but you have broken at least some bonds. So up here you have the transition state, and then you end, let me move me out of the way. You end here with the products, right? You've got the reactants over here. One thing to notice is that the number of atoms are the same, they're just rearranged. So you've got one carbon to start with, you've got one carbon to end with. You've got 1, 2, 3, 4 oxygen atoms, and you still have 1, 2, 3, 4 oxygen atoms. So all of the atoms that you start with are the same as the atoms you end with, you've just rearranged them. So to do that, you have to break bonds, and that takes energy. So you might remember a graph that sort of looks like this, right? We said progress of a reaction this way, energy this way. This is one of those energy releasing reactions. So you put energy in to break the bonds, and then you make new bonds, and that releases energy. So if you release more energy from the breaking of the bonds than you do, if you release more energy by making the new bonds than you did by breaking the bonds, then that's going to be an energy releasing reaction, like it is here. Energy releasing reaction, you can also call that an exergonic reaction. You're releasing that energy. You start with more energy, then you end with what happened to the energy? Well, it got released. So every chemical reaction between molecules involves breaking bonds and forming new bonds. And so here's the picture a little bit closer to what we were doing the other day. So the reactants have this much energy. So the y-axis here is free energy. You have very little energy here, small numbers over here. And then as you go up on the y-axis, you get bigger numbers right here. So more energy. So the reactants have a certain amount of energy. You need to put energy into the system. That's this much energy. It's called the activation energy. You need to put energy into the system to break the bonds. You've broken a couple of bonds. And then when new bonds are formed, you release energy. And so that's shown here. And then the products, in this case, have less energy. So the amount of energy between the reactants and the products, that's the free energy. It's represented by delta G, which is actually more than you need to know now for AP Bio. And this activation energy is the difference between the reactants and the transition state. So what does an enzyme do to that? Do I want to do that now? An enzyme will lower activation energy. So if you have an enzyme, you have to start at the same spot because you can't change the amount of energy in the reactants. An enzyme can do nothing about that. But an enzyme can stress these bonds, so it's a little bit easier to break them. It takes a little less energy to break them. So the activation energy is lower, but the free energy is the same. So your activation energy now will just be this much energy. Activation energy with enzyme. This one was the activation energy with no enzyme. So your free energy is the same. You can't change that, the difference between the reactants and the products. In this case, your products end lower than your reactants. The net energy or the free energy is less. You released energy. So that activation energy, this stuff here, to start the reaction, that's always or often supplied by heat. So thermal energy just means heat. So picture substrates bouncing around, bouncing into other things. Bonds are stressed when they bump or when things come together. And that moving that process, that heat energy is what usually supplies the energy you need for activation energy. Okay, so here's an enzyme catalyzed reaction. Notice that the activation energy is lower when you have the enzyme, but that the free energy is unaffected. Okay, enzymes don't affect the free energy. They just make the whole thing happen faster because the activation energy, is lower. Okay, so what does a couple of vocab words and what does this actually look like? This thing here is the enzyme, and this is the active site. So the active site is going to be the right shape for just these substrates. So here's the active site with whatever shape it has. If this is positive here and that's negative here, then not only are they physically fitting together, but chemically they'll be inclined to fit here. Like if this is positive and that's negative, or if these are both hydrophobic right here, they're going to be more likely to come together. These are very, very specific. This active site is good for these substrates, but for no other types of substrates. When you have the enzyme and the substrates together, you call it the enzyme substrate complex. And then the enzyme is going to do something to the substrates, maybe stress some bonds, or maybe put them together, the two substrates together in just the right way, or maybe take one bigger substrate and stress bonds to break it apart. But in any case, you are lowering the activation, making it easier for the reaction to happen. So lowering the activation energy. And then you have products made and they're released. And notice that you're back to the same enzyme all over again. So you're going to reuse this enzyme over and over and over again because it's not changed by the process. Okay, so another thing to know is that these are very specific. So this substrate fits right into this active site. And just like the keys to my car, I'm hoping nobody else's keys can open my car. That's pretty much how your enzymes work. They're very specific. So if this is lactose, and this enzyme is lactase, lactase breaks down lactose, and it'll break down as many lactoses as you give it, but it won't break down maltose or sucrose or any lipids or proteins or anything else. Okay, induced fit. This just means that they are specific, but once the substrate gets into the active site, this thing is the enzyme, the blue thing. Once the substrate is in there, it sort of induces the enzyme to sort of curve around it and get into a better position to actually make the reaction happen. So induced fit of a substrate brings the chemical groups of the active site into positions that enhance the ability of the enzyme to catalyze the reaction. Okay, so how does it actually do that? Physically, what is the enzyme doing? It can be doing a few different things. One thing is that the enzyme can be putting the substrates into the correct orientation so they can proceed more quickly. So these two substrates without an enzyme might take a long, long time to bounce around so that finally this side of this substrate is fitting in with that side of that substrate and a reaction is more likely to occur. So if you do have an enzyme, the enzyme can grab the pieces of the substrate, the two different substrates, and orient them, physically put them together in the right position so that whatever is on this part of this substrate is near the thing it needs to react to on this one. And they get together and react, and you make the product. So it just makes the reaction go better in some cases because it puts the substrates physically in the right position. Another thing that it can do is strain some bonds. So let's move this out of the way. So here is where we start. Here's the substrate, sucrose in this case, and here's an enzyme sucrase. And the substrate goes into the enzyme, and then the enzyme takes it and just pulls a little bit, strains those bonds, and the bond is more likely to come apart that way, right here. And then you have your two products, and then it can work again and again. Another thing is the enzyme might provide a favorable microenvironment. So environment is where you are, micro is tiny. So here's the enzyme, but this part is the active site. This might be a little bit easier to see it with this model where you can see the alpha helices and stuff. Anyway, in this particular spot, remember an enzyme is a protein, so that means there might be some R groups sticking out in here. And maybe these R groups have hydrogens on them, which is making the pH in here lower. So it might be getting more acidic right inside this area here compared to the cytoplasm. And if that's happening, maybe that's what's needed for one particular chemical reaction to happen. There might be another enzyme where the active site is more hydrophobic, and that might be what you need for this other microenvironment to make the reaction more likely to happen. Or maybe the active site of yet another enzyme makes that little microenvironment a little bit more basic and makes the reaction more likely to happen. Okay, another thing that happens, which is so weird, is that sometimes the enzyme will covalently bond to the substrate, which you would think would be not really what would happen for an enzyme because enzymes are reusable. But as long as you break that bond by the end, it's all okay. So chymotrypsin is not named right. Should be named with an ACE. It's not, but anyway, chymotrypsin is an enzyme. This enzyme is a protein, like most enzymes. One of the amino acids in the protein is serine, and so serine has this OH on it. That O has these two electrons, which will bind here with carbon, which means carbon is only supposed to have 4 bonds, and so this bond will go away and the electrons will come over to the nitrogen, so it'll look more like this, and it'll grab another hydrogen. And so, well, the hydrogen actually can go, oh, it goes over here, but this one will grab another hydrogen. And so that's catalyzed the reaction that breaks this thing apart. And then later, you'll break the bond right here. But this is the first step of covalent bonding. Okay, other important stuff. Oops. Only small amounts of enzymes are needed because they're used over and over and over again. So here's an enzyme. Here's the substrate. They go together. In this case, it's catalytic because you're breaking one molecule down into 2 smaller molecules. But notice that the enzyme at the end of all this looks just the same as it did in the beginning. So it can catalyze this reaction over and 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 over over and over and over. Okay, enzymes are not permanently changed in the process. So here's the substrate, induced fit, so cool, right? There are the products, and oh my God, the enzyme's back to do it all over again. Go enzyme! So the enzyme keeps catalyzing that same reaction over and over and over again. Okay, this graph, I think this is what I'll end with. This graph is super important. You'll see this a lot, this type of graph a lot on an AP Bio problems. So what we're looking at here is sort of like the lab we did the other day. So remember how we had test tubes? Oh my goodness. Well, okay, we didn't. We had cuvettes, but test tubes are a little bit easier to draw. So we've got a bunch of test tubes, and in each test tube, we're putting the same amount of enzyme. And we put an indicator in them all too. So that was stuff that was constant. We were putting those in each test tube. Pretend I drew the test tubes the same. Anyway, in this one, we put no substrate. And remember, it didn't change color because there was no substrate to turn into a product, so we didn't get any color change. In these, you're adding more substrate, but varying amounts of substrate, right? A little bit of substrate to more. So vary the substrate. So that's your independent variable. So substrate concentration is on your x-axis here. Reaction rate is on your y-axis. This is what you're measuring. It's the dependent variable. So reaction rate just means how much product have you formed over a certain amount of time. So I want you to be able to think through this graph. If you have 0 substrate, then you're going to make 0 product, right? The way it works is you have a substrate and an enzyme that makes the reaction go. You might have a couple substrates, right? And you're making a product. If you have 0 substrate, you're going to make 0 product. And so that's what's going on right here. That's why it starts low. And then what you can see here, this picture, I think it's kind of nice. It's showing 3 enzymes here. And then over here, it's showing you a medium amount of substrate with, again, 3 enzymes. Same amount of enzyme in each tube because you're only supposed to change one thing, right? And then here you also have 3 enzymes. Okay, so what happens when you have a fairly low concentration of substrate compared to a high concentration of substrate? With a low concentration of substrate, the substrates, they're just not too many of them. They're bouncing around. Sometimes they get into the active site and product is made, but the enzymes aren't working that hard. They're only like once in a while a substrate comes in. So you have a fairly low reaction rate here. As you get more and more and more substrate, you're getting a higher and higher and higher reaction rate. Finally, you're at a point where you have a lot more substrate and the enzymes are working pretty hard, not as hard as they possibly can, but more often than not, there's a substrate in the active site and they're making product they have a fairly high reaction rate, making pretty much a lot of product per second or whatever, right? And then the weird thing is it levels off. So when you have a very high substrate concentration, like let's say you're right here. At this point, you have so many substrates that your enzymes are constantly working. The substrates are in those active sites like almost pretty much all the time. So the enzymes are going as fast as they can. It doesn't matter if you add more and more and more and more and more substrate because the enzymes just can't process anymore. The analogy I usually give is I used to work at the mall when I was a kid, and most days would be, no problem. The lines wouldn't be that long, and I would be able to, to take care of the customers, right? Around the holidays, sometimes there would be like 40 or 50 people in line, and they would all be mad at me. But like I could only ring people up as fast as I could ring them up. The only way we could go faster is to get more cashiers. And so sometimes someone else would join me and would have more cashiers. So with a given limited amount of enzyme, you can only go so fast. The enzyme active sites are filled up. We call that saturated. We say the enzymes are saturated at that point. They are going as fast as they can. Their active sites are as fast as they possibly, or are working as fast as they possibly can be. The active sites are all filled up. All right. See you next time.